In this video, I will explain how to transform a block-structured mesh into a NURBS mesh using TAFSM software. The whole process is summarized in this scheme. As you can see, the first block is called CGNS. It tells us that TAFSM software requires the block-structured mesh to be in the CGNS format, where CGNS stands for CFD General Notation System. CGNS files are topologically based. That implies that a file in this format is organized by zones, and each zone contains similar information, such as grid coordinates and multi-zone interface connectivity. For a block-structured mesh, the zones represent the blocks. If you're using pointwise to generate the block-structured mesh, when you export a CGNS file, it will automatically write the blocks into separate zones. TAFSM software puts all the data from a CGNS file in the finite element format. It creates separate files for nodal positions, connectivity information, internal and boundary elements, boundary conditions, and material information. This conversion is shown as the first step in our scheme. After this, the finite element mesh is transferred into a NURBS mesh in Bezier extraction format. This is done by means of several projections. To properly address the projections, we first need to discuss NURBS basis functions, because NURBS basis functions describe the relation between the finite element and NURBS meshes. Here we see an illustration of the NURBS basis functions corresponding to the above one-dimensional finite element mesh. The question is, how do we construct these basis functions? On each patch, NURBS basis functions are defined by the node vectors of the patch. In fact, each block is viewed as a forerunner of a NURBS patch. And to relate a block to its corresponding patch, we define a common parametric space. If we choose an interval from 0 to 1 in all three directions, and let the order of the NURBS basis functions be denoted by p, then the node vector in each direction will start with p plus 1 zeros and end with p plus 1 ones. Let's write down these components. The TAFSM software finds the remaining node values using a method which is called parametric spacing proportional to physical spacing. This method defines element length HE for each element E and uses cumulative sum of the element lengths denoted by SE. The remaining node values are then equal to normalized cumulative sums, and the node vector looks like this. For the finite element mesh which I had shown previously, the first non-zero node value is equal to H1 divided by the total length of the interval, which is equal to L. And the second non-zero node value is equal to H1 plus H2 divided by L again. Let's return to the projections. For each patch, the projections are performed hierarchically. First, the control points at the corners of the patch are set to the same locations as the corner grid points of the block. Then the edges between the corners are projected by using the common parametric space. More precisely, the position representation in the patch is found by solving this equation. Here, WH is the test function, XH represents the position in the patch, which is the unknown, KH represents the position in the block, and Xi is the parametric coordinate. Once the projection of the edges is completed, we proceed with the projections of the surfaces between the edges and the volumes between the surfaces. These projections are multidimensional versions of the projection used for the edges. For more details, we refer you to a paper by Otoguro and co-authors from 2017. I will provide the full reference in a second. I just want to return to our scheme once again. The final step in this scheme merges the control points over a shared surface between two adjacent blocks. It's a very important step because it ensures that the projections result in the same control point positions. And this leads to C0 continuity for the basis function across the surface. Finally, I want to address the Bezier extraction format. As it was mentioned previously, the generated NURBS mesh is put in this format, and there is a good reason for that. NURBS basis functions possess many useful mathematical properties. For example, they are non-negative and satisfy the partition of unity. However, it is a well-known fact that the support of higher-order NURBS basis functions consists of multiple non-zero knot intervals. This global structure complicates the integration of IGA into traditional finite element context. To avoid that, the Bezier extraction format is used. The Bezier extraction operator decomposes a set of NURBS basis functions into Bernstein polynomials. The Bernstein polynomials are formed by a knot vector with no inner values. The use of Bezier basis functions allows to construct curves that are geometrically equal to those constructed with a B-spline basis, but the support of Bezier basis functions is localized to a single knot interval that allows for a much easier integration of NURBS in FEA setting. This completes the theoretical part of this video, and here are the references that I promised you previously. To see how the pipeline works in practice, we are going to return to the frustum geometry that was created in one of the earlier videos. At this point, all we have to know is how many blocks form the block-structured mesh, and the easiest way to check that is by reading it off from the list of blocks in pointwise. In our case, we see that there are only 5 blocks. So aside from this piece of information, we just need our CGNS file, and I already have opened the directory that contains it. Here I also have a short script file that allows me to convert the mesh to the finite element format. Let me show it to you. What we have here is the CGNS to TAFSM command that is placed within a for loop. And the for loop runs from 1 to 5 because we want to apply the command to all 5 blocks. We obviously have to specify the name of our CGNS file and the output directory. I'm asking to store the output under mesh_fam, and within that directory to store the output for each block separately. If you need to specify other options for this command, you can find them in the help message. It will give you the list of the existing options and the corresponding description. And this is how it looks like. Okay, let's convert our block structured mesh to the finite element format. So this is a very small example. That's why the conversion process is already finished, and we can take a look at the generated output. So we go to mesh_fam, and here indeed we see 5 blocks. So let's go to, let's say, block 2. We see several files here. Mesh_cfg is the control file. It describes mesh information and locates additional files. Let's take a quick look at it. Here, the first thing we see is the version that was used, then the number of nodes, the number of elements, some technical information on the storage of the binary files, and the offset tells us the ID of the first node. It can be either 0 or 1. Then we have the number of parametric dimensions, NPD, the number of spatial dimensions, NSD, and the number of element nodes. After that comes the list of additional files. The first file, mxyz, contains information on nodal positions. The second one, mien, tells us the connectivity information, and the last one contains the boundary numbers for elements. In this file, negative integers refer to interior boundaries between elements, while positive integers refer to the domain boundaries. We see all these files back in our directory, and there's also an additional boundary.txt file. This file describes if a boundary is an inlet, an outlet, or a wall. So we've looked at the files which correspond to block 2, and that is actually sufficient because the files for other blocks are very similar to these ones. Next step is to convert the finite element mesh to the NURBS mesh in Bezier extraction format. And for this purpose, we are going to use the E to B function. So let's return to our main directory. This time we need FE to BEF file. As you can see, E to B does not require the use of a for loop, but we do need to provide it with the number IDs of the first and the last block that we are considering. In addition, we specify the path to the block meshes, the output directory, and the number of integration points. And -C simply asks to print the output in color. Okay, we are ready to run this. It's a little slower this time, but that was the last block. Let's go check out our mesh_Bezier directory. Here we see that we don't have blocks anymore, we have patches, and we have an extra subdirectory that combines the patches and has an appropriate name, combined. This time I'm not going to dive into the output files because they are very similar to the ones after the next step, after we eliminate the redundant control points. So this brings us to the merging part. The command that is used for merging is called merge internal, and all it requires us to do is to provide the control file of the combined mesh, which is page.cfg, and we have to specify the output directory, and that's all. Let's run it and take a look at the output files. The control file remains page.cfg. It is very similar to mesh.cfg, but it does contain additional information on the extraction operator. The remaining files are similar to what we saw under mesh_fem. However, there are some new files as well. I'm going to focus on those new files. You might already have guessed that CXYZ file contains the positions of the control points, and order indicates the polynomial degree of the basis functions. C obviously refers to the Bezier extraction operator, and C_offset indicates the start position of each element in the C list. Finally, IEN_offset indicates the start position of a new element in the MIEN list. I also want to briefly show you a command that lets you check the mesh quality. Let me run it. The main purpose of this command is to identify elements with a negative Jacobian. And as you can see, in our case, we don't have any invalid elements. So no elements with a negative Jacobian. And this concludes our session on the transformation of a block structured mesh into a NURBS mesh using TAFSM software.